listening to beautiful talks. So I put some pictures of beautiful Edinburgh that I found while I was looking at the map, not outside. So on the left there, you have the Braid Hills. There's a golf course, so of course I had to put it on there because it's Braid. And then on the right is the Hermitage. I'm not sure of the pronunciation of Braid. So there you go. It's got Braid in it. That's why. This is joint work with Pablo Galatian, Thomas Lamb, and Mintam Trin. So there are really going to be two parts to the talk. The second part will be for the people who are allergic to type A. I know they're out there in the audience. And the first part will be for everyone else. The first part, what I'll do is I'll tell you a story. I'm not really an expert in the story. There are a number of intimidating experts in the room. So if you are an intimidating expert, then feel free. I'm sure you already. I know that you feel free because to let me know where I've gone wrong. But anyway, so the story will be that we. Even if you're not an intimidating expert, feel free. So I'm going to start with maybe some knots, some links, and then we're going to fancy it up, and we're going to make it into braids, and then we're going to fancy that up even more into braid varieties. And the reason for this is that this knot somehow knows something, and I want to know why it knows that thing. So let's see if we can get going here. So we're going to start with the knots or the links. Okay. All right. The structure is good. So here we have, this is Haken's Gordian knot. So the Gordian knot was this fabled knot where if you were to unravel it, you would rule the world. So Alexander the Great was presented with this knot, and he unraveled it by slicing it with his sword. And he went on to rule the world, so it worked out pretty well for him. So the central sort of question, oh no, actually, is Teo here? Yeah. Oh, should we do a bet? Do you think? So the central question in knot theory, the central question I think is is it a knot or is it not a knot? Is it the unknot? So that's the question here. That's what's posed. And so well, yeah, we yes. Think about it. Yeah. No. Yeah. Yes. And so it's kind of hard to answer these questions, right? Because you're presented with what is the knot projection, and it's not clear if you can unravel it or not. What can you do?
It's not clear.
It's not clear. So okay, Rademeister moves. Enough said. So the first thing that you try to do is you try to write down some invariants. So these invariants could be a number, they could be a polynomial, they could be something, just something that doesn't depend on how your knot is projected. Yeah. And so the classic first example would be to distinguish the trefoil knot, that's the one on the right, from the unknot, because the number of tricolorings of a knot is an invariant under these Rademeister moves that we discussed in some detail in the last slide. And so the way that these tricolorings work is that at each crossing you want to see either all three colors or only one. And if you're an intimidating expert just coming in, feel free to jump in. And the point is that there are more of these tricolorings of the trefoil than there are of the unknot, and so we've distinguished the two. Okay, so you try to write down invariants, and people try to write down invariants, and they get better and better invariants, and at some point you get to the Homfly PT polynomial. So this has quite a long name. The reason for this, so what you see here is the footnote on the first page of the paper that defined the Homfly polynomial. So there were 4 different groups of 6 people, and then 2 more, the P and the T, who were, because of the Cold War, I guess the Postal Service was slow. So there were 4 different groups, and they all developed the same knot invariant. Okay, so this is the story, and it's in the footnote there. So they all submitted the same paper at approximately the same time. And so then the editors decided to merge the papers. Everyone wrote a section. So here you go. Here's the definition of Homfly. It's done by these skein relations, right? So if you have a crossing, then you can rewrite in terms of the other kind of crossing or no crossing, and then there are various bits of well, there's a Q and an A and whatever. But this is picking up some information, and if you specialize A and Q in the right way, then you can get famous knot invariants that existed before. So somehow this was very powerful knot invariant. Okay, questions on this?
Maybe can I make a learned comment?
Please.
So the first invariant and the Alexander polynomial
are defined in terms of the complement, so the invariance of the complement, whereas the Jones is not known what is the invariant of the complement.
On the complement of the knot.
Yeah, it's defined in terms of a projection,
I see. Yes.
but you don't know whether it's the invariant of the fundamental group or of the complement.
Okay. And that is different, a different Alexander than Alexander the Great.
Really?
So, so I'd like to define a knot here, a class of knots. These are the torus knots. So here's the picture. Draw an n by p rectangle. Draw the main diagonal, and then, well, make it a square, then make it a torus, and then view that as a string in space. This is the torus knot. If n and p are co-prime, then this will be a knot. Otherwise, it will be a link. And so now I will put for you this calculation of the Hamfly PT polynomial of t of 2, 3. So t of 1, 2 is just the unknot. So that's just 1 by definition. So t of 2, 3, it's not so bad. So we just pick a crossing and we sort of resolve it in this way. And then this one's already trivial. And then you resolve this one and you sort of go, and by the time you're done, you get this this polynomial in A, well, A and A inverse and in Q. Yeah. And so the interesting thing here is, so we started out, we had 1, and now if we look at this top coefficient in A, then we have this Q analog of 2, and so it makes you wonder about what happens with T of 3, 4, 4, 5, maybe n plus 1. And so, you know, the question for the audience would be, do you know a sequence that starts 1 and then 2, and what the next number is in that sequence? And you're right, it's 5, because it's the Catalan numbers. So there you go. Here they are. 42. Right. These have occurred. And so basically every combinatorial object is a Catalan. Is counted by a Catalan number. So we can actually write down the coefficients of the Hamfly PT polynomial, the A coefficients, and they turn out to be well, these sort of rational Kirkman numbers. Okay, so these polynomials in Q, and these appeared in Teo's talk for the K n plus 1. These occur in this very nice paper of Rainer Scheffler and Eric Summers. Yeah, so just to note, that is a very special case. When you have the torus knot n plus 1, then you get on the nose the Catalan numbers. Okay, and this is basically some motivation here, because it's like this knot seems to know about Catalan objects somehow. How does it know this? So somehow these objects must be hidden inside of the knot, and I would like to understand this, and then I'd like to generalize it, and so on. Okay, so the knot knows about Catalan numbers, and that's suspicious because it's just a trefoil, like it's just a piece of string. So we have to make things fancier. So we'll go to braids. All right, so there's a correct presentation of the braid group, and
I don't understand what this is.
and so we have some pictures of braids. Sorry, Theo. Okay, so what is the relationship? Well, it's pretty clear. You take a braid, you fold it up, and it makes you into a link, like so. And so every oriented link arises in this way, but of course it's not unique. There are these Markov moves that relate things. So for example, what you can do is, since you've completed it, you can rotate the braid, and this is like conjugation in the braid group, so it's invariant under that. And then there's also this little loop thing that I've drawn here. And that's just adding like a generator at the end. So so we can go from braids back to the land of links or knots. And so what we'd like to do is we'd like to read off the invariance in terms of the braid. That's the point. But okay, if we're going to do that, then anything that we write down, it better be invariant under conjugation and whatever this Markov move is. And okay, so this is so you can see there's an A, and so one way to try and get well, I've got a suspicious Q in there already. So one way to try and get that into the story is to pass from the braid group down to its quotient, the Heck algebra. And so just a quick reminder of the Heck algebra. So it's a quotient of the group algebra of the braid group, and under those relations. And of course, it has the basis indexed by elements of the symmetric group. It's a deformation of the group algebra, and it has the same representation theory as the symmetric group up to these Qs. This is the point. So the theorem is that the Homfly PT is the unique Markov trace. However, I don't really want to work with Markov traces. I'd rather work with sort of this unique symmetrizing trace where I just, if I'm working in the Heck algebra, I just want to pick off the coefficient of the identity. Okay, so that's sort of it's not quite as powerful of an invariance, but what it does is it does pick off the top coefficients in A for me. It doesn't pick off all the coefficients in A, it just picks off the top one. But this is the one that's I'm going to be able to do geometry on. So I want to use this this very special trace where I'm only taking the coefficient of the identity in the Heck algebra. And in fact, recently Tom and I came up with this proposition where we can actually construct, we can get the other coefficients by summing up various of these canonical traces in this way. And there are well-known representation theoretic methods for computing these traces by summing over irreducibles, and of course you have these weights. And I apologize. I have misspelled his name. I don't know how this is possible. So let me just fix that. Otherwise, I'll feel really bad. There we go. My goodness. Okay. Okay. So that's Mintom. Sorry. I apologize, Mintom, if you're watching this. Okay. It's pretty inexcusable. Okay. So now I'd like to do the same calculation that I did for you using the definition of Homfly, but I'll do it in the Heck algebra. Well, I won't do it, but I'll show it to you. And here it is. So I'm trying to compute the same thing. So I've got this. So I'm trying to compute the Homfly of the Braid closure of this Braid SSS. I'm just in type A1, S2, and so we already know it's that because we computed it using the skein relations. But now what I'm supposed to do is I'm supposed to take the coefficient of the identity inside this element of the Heck algebra, and we just compute. Okay, there it is. I'm not going to read it off for you. And again, you get the two coming out. So it's the same two as before, but now I didn't have to like choose a crossing. I didn't have to, it's much more algebraic. So it seems like we're making some progress. Okay. And so now we've sort of transferred our problem. So before the problem was that the knot knew about the Catalan numbers. Now we have the problem that we have a braid that seems to know about the Catalan numbers. And I'd like to find the Catalan, some objects hidden within now this braid. Okay, and generalized in various ways. This is what I would like to do. Okay. So we need to make it fancier. So we go to braid varieties. So here's the philosophy. SN has got a bunch of stuff with it. It's got the Lie group, the Braid group, the Heck algebra we already discussed, all sorts of things. And in particular, I'll be working with this particular Lie group. So we have the flag variety. We have and then we have relative position. So flags, I've drawn a picture. It's like a flag, and then two flags are in relative position, given by simple reflection if they differ in the I and I plus first position. Is it clear? So now we're able to, okay, so now we're going to do an example, right? So for SL2 FQ, it's very simple. You can just write you can write the entire flag variety down. You can write down all the Borels, and basically everything is in relative position, the identity with itself and the simple reflection with everybody else. So it's quite simple to understand what the flag variety looks like in this case. And this is enough now to define the braid variety. So what we're going to do is you should sort of think of this beta 1, beta 2, beta. This is like our braid, and what I'm insisting is that I have the sequence of Borels, each of which is in relative position, given by these simple reflections to the previous one, with the condition that I start at the canonical Borel, the positive, and the last braid in my sequence has to be in relative position, the longest element to the negative Borel. And that's the braid variety, and you can also twist it by an element of the Weil group in the following way. So it just twists the first Borel, and also twists the relative position requirement on the last Borel. So we started with a knot, and we went to a braid, and now we've got a braid variety.
So this is a generalization of what Samuelson variety.
That's right. Yeah. So I'm going to be putting just simple reflections on the as my relative positions, but you could condense things and it all would work. Yeah. Okay, so now I want to do the same calculation again for you of this torus knot, but this time with the braid variety. So the point is that this braid variety is going to encode that top the coefficient of the A, that Q version of 2. It's going to encode it as a point count now. I'm working over a finite field. I have a space. I can count the number of points. And that's going to be giving me this Q analog of 2 that we've been seeing. And so we just sort of decompose it. I guess you can look to see where the B minus is going to be. It can't be in the third position, so it can be in the second or the third. And you sort of write down enough conditions, and you can compute the number of points, and you get the same answer. And of course, that's a true statement. That this braid variety, if you count the number of points, actually encodes that top coefficient. Okay, so we've made some progress.
You have Q-1 extra factor, right?
Yeah, so there's some factor. We're not gonna, well, we'll worry about it in a little bit when we try to do combinatorics, but it's an extra torus, and you could kill the torus earlier in life, but then the definitions would become more complicated. So I've decided to squeak it in there. Yeah.
Is that any kind of like self decomposition or paving, what you did where you broke it up according to the B?
This one, the one that I chose, this may actually be this is the Diodar, and I'm getting to it. Yes. Okay, so this is the picture that we have. And it's okay. So it's telling. So I've kind of answered the question in the sense that now I've got it as a Q count. So it's sort of explaining why the knot knew about this. But now I'd like to do a little bit better. Oh, okay, so we can also do the other coefficients because we were able to write down whatever. This is far too complicated, so it doesn't matter. Right. And so I still it's not answering my question as a combinatorialist, which is I actually want to find combinatorial objects inside of here. And right now I've just got like a point count and Qs, and that's not actually combinatorial objects. So I'd like to find the combinatorial objects, like non-crossing partitions, like what Teo introduced. And so let's do exactly what Vic was suggesting and get to the decomposition. So so there's a way to decompose. So we need to have some conditions on words. So you look at subwords. So the subwords of the initial word that's encoding these relative positions. And the way that you do these subwords is you just choose the letter or you don't. And you want the product to actually be 1 or W if it's the twisted version, but don't worry about it. And you want to have distinguished subwords. The distinguished condition is key. This means that essentially you go down in weak order or Bruchau order or whatever when you can. If you can go down, then you must go down, is the mantra. And then the maximal distinguished ones are they're going to be the ones that use as few ones as possible. And if you use as few ones as possible, so I put the two sets of these combinatorial objects at the bottom here. So here are all of the distinguished subwords, and here are the maximal ones because they use only one, whereas this one used 3. And in particular, you'll note that S1S is not in either of these sets because if I go up by S, then the next one I could go down, so I would have had to go down. And so this is not a distinguished subword. Questions on distinguished subwords? And so this is Diodar's decomposition of the braid varieties that decomposes in this way. And in particular, you can even read off what the point count of each of these components is. And so I'm now doing the same computation again, using the Diodar decomposition. So this is the same Q version of 2, where now I'm taking this braid variety and I'm decomposing it according to the Diodar decomposition, and voila.
So these are irreducible components.
What's this?
Are they irreducible components?
This I'm not sure of.
Okay.
Nathan, this might be premature, but
Yeah.
I mean, you have a Q analog of the Catalan number.
That's right.
Have-
Yeah, that's what this is the Q analog of the catalog.
This will actually
This
be,
is the Q analog, yeah, as a point count. That's right.
I was asking, I wasn't.
Yes, yeah, sorry, yeah, that's well, yeah.
Just a second, I have trouble moving the last identity, the last equality.
The last equality.
Like left-hand side is divisible by Q minus 1 squared and the right-hand side is not.
Yeah, this is true. This is true. Let's see.
You felt bad. I had a typo in the slides and he added one as well. Thank you, Nathan.
That's right. Thank you, Tayo, for that. Yeah.
So what is it supposed to be?
I believe that it's supposed to be what is on the right hand side, and I also believe that it's supposed to be what's on the left hand side. Yeah, we're gonna keep going. And,
Yeah, keeping
I see the problem.
exponents one.
What's that?
It's counted.
Exponent.
I mean,
We want
Either
to switch one and two. One and
Yes,
two.
I think I have to switch the 1 and the 2. I think that's the point. Yeah, that's exactly the point. Yeah, the q, it should be q squareds. Thank you, Pavel, for that. Okay, right, so now I can get to the combinatorial objects. Right, so here's the point. We have these maximal objects, and the maximal objects, in fact, this is how very instructive that I messed it up. But so the maximal objects, these are the two maximal distinguished subwords, and they sort of have as few q-1s as possible. And so what we can do is, if we're dividing by this q-1 on the left hand side, then what's going to happen is we're going to be left with these terms that all have a factor of q-1. And then as I send q to 1, these will all vanish in the appropriate way. And so that if I do this particular construction, I'll end up getting just the number of maximal distinguished subwords.
But again, in the last example, we have to correct, yes?
In this last example, yeah, because I shouldn't be dividing by q-1 squared. This is nonsense. I have to divide by q-1. Yeah, thank you. That's right. And yeah, and so now, but now we've actually so now we've taken this braid variety, we've decomposed it into these pieces, these components, and each one of these is indexed by a combinatorial object. As we send q to 1 now, we're actually getting the combinatorial objects on the nodes. Okay, so we have to discuss what these combinatorial objects are. And
Certainly components.
is there another question? Okay. Okay, so there are the non-crossing partitions. And so let's see, this has been yeah, it's getting a little late in the day. So there is an easy bijection. If you want to see it, I've done it here in the slides probably correctly, although who knows. You can also look at our paper. I first learned about this sort of bijection from a paper of Christian Stumpf and Vincent Pilot. It's in a remark, so you can also go check out that paper, probably of subword complexes and brick polytopes. So there's an easy bijection to non-crossing partitions, and perhaps we can leave it at that. And there it is. It's still easy. Okay, so this concludes.
Partitions and
Sorry.
bijection between subwords.
Oh, the maximal
Subwords,
distinguished
subwords.
subwords, the maximal distinguished subwords for this particular braid and the non-crossing partitions. And here it's just at the level of combinatorics, but the punchline will be that all of this extends to other types, but I'm getting there because we're still in the part for the people who aren't allergic to type A. Other questions, other complaints?
Did you say C is the Coxeter or not?
Yeah, this is the braid that closes up to give you the course now.
Okay.
I mean, I didn't say it, but it was written in the slides. Yeah.
It flew by so quickly, these slides.
Well, there are more.
I'm going to spot something.
I'm trying to go so quickly that no one notices the errors.
But the mistakes if it goes that.
That's right. I can take other questions.
Oh, keep going, come on.
Okay. Perfect. All right. So okay. So now we'll do some well for this crowd, actually I don't have to.
Oh, no.
Let me just show you the slides here. So we have Q, we have R. I note that we lose some stuff between going from Q to R, and then we lose some more when we go to C, and that will come back in a little bit. Okay, fine. And there's classification and there's invariant theory. I think there have been this slide how many times already? So there it is again.
Can you show the first one after the evangelism?
There was a mistake.
This
Yeah, and the next.
and the next one. And the next one.
Yeah.
Is it okay?
Yep.
I'm presenting the Coxeter group, not the Braid group there.
Yeah.
That's a good one.
All right. So blah, blah, blah. Okay, great. Complex reflection groups. Yeah, so this one's hard because you lose the geometry. This will come back. The great thing is, you can play with objects that don't exist, and talk about spaces. I mean, you will be unable to make braid varieties, but one could still do the computations that count the number of points in these braid varieties, even though we don't exist. So that will be fun. We'll get there. Yeah, right. Diagrams, and then this thing. Yeah. All right, and then maybe just to emphasize, since I had this explained to me like earlier in the conference, maybe it's not as well known, but I grew up on this stuff. So right, you want uniform proofs, yeah. So depending on the level of generality, you want uniform proofs, and what this means is it doesn't appeal to the classification, and of course, whatever level of classification you're talking about. And there's an example of a beautiful uniform proof. These slides will not be made available after the talk. Okay, so let me get to this example now, and this will be at the level of real reflection groups. Okay, so we have the Coxeter Catalan numbers. Okay, H is the Coxeter number, E, I are the exponents, DI are the degrees. There's the Catalan number again. But do you want to check that I didn't make a mistake on this one?
Yeah, but so why did you write like that? So you want to EI is DI minus 1, so
Yes, but if you do rational versions in complex reflection groups, then you'll need to make some other modifications. So. All right, so we have right, the non-crossing partition lattice, that's fine. And of course you have this standard isomorphism. I guess we probably don't need that. Okay, great. And I guess the point was, of course this sort of all goes back to Reiner, to Vic Reiner, although he'll credit Rika Simeon for this type B stuff. But then there's this very influential paper that Vic had. And if you count the number of non-crossing partitions, then it has this beautiful formula. So that's the point. We had the number, but we also have the objects, and the objects are counted by this number. And what's very frustrating, and was very frustrating for a long time, is that the proof is not uniform. So the way that you do this is you make combinatorial models of the non-crossing partitions, much like you do in type A, and then you do it for B and D, and then you do computer checks in the exceptional types. And so, like, just as a remark, for example, the number of clusters in a finite type cluster algebra, that's a non-crossing Catalan object. So that was not uniformly known to be counted by this product expression. It was only known case by case. And let me just say there are some generalizations of the Catalan numbers that are possible, and there's sort of two axes. So one of them is the type axis. This is pretty easy, I guess, once you have the right definitions, thanks to Basis in the non-crossing objects, and you can go all the way to well-generated complex reflection groups. You also have this parameter axis. The parameter axis is going to be tweaking, instead of the H in those formulas, you'll see an MH showing up. So you work your way from Catalan to Fus Catalan, and then maybe eventually to rational. And of course, the rational non-crossing objects, well, no one could define these. I'll talk about that in a second. But for non-nesting things, it's very easy to go in the parameter direction, because you take the Summers region. I put that there to remind myself to say it. The Summers region, and you dilate it in various ways, and you can easily get the parameter axis for Weyl groups, because you need an affine Weyl group there. And so of course then it doesn't generalize to like H3, and complex reflection groups are off limits. Yes, please.
I'm just curious because P is not prime to the Coxeter number. It's actually a true rational.
Oh, no. That's the name for it. But yes, it's prime. It's relatively prime to H. Yeah.
Okay, and that's just what we call rational because of the. I got it.
so rational means MH plus R plus something rather than 1. Yes,
Sure.
But R is prime to H or
Absolutely. Okay, so let me just sort of give you a brief history of the non-crossing partitions, but this is in the type axis. Okay, so we have Creveres, Montenegro, Reiner. Okay, so I didn't even put. I see. Okay, well, okay, then the Berman-Coley and Braid, Picotin, and Basis. So all of these. This is a very quick history. The literature is extensive. I could spend forever on that. So there's.
I feel like Heyman should get some credit too. You're right.
Well, it's non-crossing partitions.
Okay.
Non-nesting.
Maybe in the earlier slide.
Not nesting. Yes. Wait.
What about the Catalan number?
The W Catalan number. Yeah, but I'm doing particularly non-crossing partitions. Yeah,
I
okay.
should have complained earlier. So
Okay, oh, sorry, okay, yes.
Can you show the previous slide?
I
please?
can, This one,
Can you put H on the red axis?
yeah, what do you need?
Quaternions.
Hamiltonian.
Oh, yes, that's lovely. I love it. Yeah, let's just extend that arrow. And this is good. Talk is getting better. I guess we do this again tomorrow, right? Okay.
No, but is there anything corresponding to that?
Periodic reflection groups. I don't know anything about them.
Was that you on there too?
Oh, yeah, for you, of course. Yeah. But that's it's a branch or something. Hold on. Okay. There we go. Something like this. Okay. Other modifications. No? Okay, good. Yeah, so here you could complain that Haman should be said because of section 7 of the quotient ring of diagonal harmonics. Yeah. Okay, so anyway, I'm talking about objects here and counting objects, like honest to goodness objects, and wanting them to be counted by the Catalan number. I'm trying to present. There are going to be three problems in Coxeter Catalan combinatorics that have sort of dominated the last I don't know how long. Okay. Also, we have to talk about and by the way, note I only did real type. Okay, so sorry about that. And then there's the real parameter history of non-crossing partitions. So yeah. Okay. So here's what's happening is we're trying to do the Fuss versions. And no, I'm only doing non-crossing partitions. Right? I'm not talking about Euler and Fuss himself. So okay. So we have Creveras, and then Edelman has this beautiful paper on chain enumeration and non-crossing partitions, and then Armstrong's thesis where he does this in does Edelman's construction, but in all types. That's his thesis. It's very beautiful. Okay. So the point is though, you have these non-crossing objects. You'd like to have objects that are counted by this P coprime to H. Yeah, and so you can see see the slight lie there. And the point is that as you have to twist a little bit sometimes, yeah. Yeah, so right. What's that? Yeah. So and so this is always an integer. And so I first learned about this problem from Drew, which was, give me a non-crossing object that is counted by this number. We want the objects. Okay, and this is a problem because, like, for example, the construction that Edelman came up with and that Drew generalized was you're looking at the non-crossing partition lattice and you're taking like multi-chains. Okay, so chains of elements that are all comparable. How does this generalize to like when M is 2? Then you get you're supposed to take two elements in succession. But how do you do this for this rational parameter? It doesn't really seem to work. The fractional multi-chain doesn't make sense. And Christian and I tried all sorts of things back in the day. This is a picture of Drew, by the way.
You're on the left.
Yeah. The one with the long ears, or the one with the short ears?
Yeah. So these were the big problems with the Catalan stuff. So one was the uniform enumeration of the non-crossing partitions. One was the construction of rational non-crossing objects. And what I haven't really talked about, but I mean, we sort of mentioned it and we omitted Haman and when mentioning it, where there's a bijection between the non-crossing and the non-nesting. And so we resolved the first two of these in this work. So the point is that these Braid varieties, their point count, and you can prove this uniformly. I'll have a slide on that in a second. The point count is given by some Q version of this rational Catalan number up to those Qs that were bugging you earlier. And so of course then if we do this same Diodar decomposition trick where we cut stuff up and then take the limit so that we're only getting the maximal ones, then we actually get the combinatorial objects that we wanted. Yeah, and so in particular in the case of H plus 1, in the same sense as there's an easy bijection to non-crossing partitions or even Fuss non-crossing partitions. Okay, so the proof method.
Can I ask about this formula?
Yes, please.
It's the denominator is more or less the order of the Lie group.
Yeah.
Yes.
Yeah.
So is there a kind of this variety? Is it a quotient by G of something where it acts freely? Or at least can you replace it with something like that?
Yeah, I mean,
And
I
a
don't,
similar question about the non-QD form. This is order of the while group. So yes, can you produce some set on which our while group acts freely and has order equal product of the numerator?
yeah, so that one I can say that's Heyman's construction. So that one does work. Then it sort of makes sense. You need the P co-prime because it has to do with the root lattice. For the Q version, I'm afraid I have no answer for you. Yeah,
As a Hilbert series.
Yeah, that's a different.
yeah.
I'm asking about the finite field.
Right, it's a point count, and yeah, it seems natural that yeah, maybe there is a free action on some space given by the numerator. I agree.
I mean, I'm inserting myself, but the Lustig has a paper, intersection cohomology complexes, blah, blah, blah. And I wonder, do you use that paper in the next slide, or that's not?
Well, we use very heavily Mintam's thesis. So if the thesis relies on that, then
Because it has similar formulas, maybe.
yeah. So yeah, I mean, we basically cobble together things from Mintam's thesis, the Gordon-Griffith computation, where they make this complex and compute, but they're doing stuff for the rational Cherednik algebra. And then the combinatorics that Christian and Hugh Thomas and I had worked out earlier. And the key thing here, by the way, this is a crazy formula. This is Lustig's exotic Fourier transform. And so these are fake. The DEG or the FEG are the fake degrees, and these are somehow related to those Schur weights that we were talking about that decompose the Hecke algebra. And so I just want you to note that. Here I'm plugging a root of unity into this one and a Q into this one, yeah, and then I've swapped it, and it's the same. And these are both computing the trace of some Hecke algebra element. And what else did I want to say on this? Yeah, so this is oh yeah, so the point is that actually on the left-hand side, since this is somehow related to the Coxeter element, there it sort of is non-vanishing on H, the Coxeter number, many irreducible representations. When you do this trick, now it vanishes on all but N. These are the exterior powers of the reflection representation. So it cuts down substantially. And then the formulas look like the ones that Gordon and Griffith had written down. And we'll skip this slide. This is the combinatorics that you don't want to see. And you can also do parking functions. So if you glue together these twisted, so these are the rational parking functions of parking spaces, which was Armstrong, Rhodes, and Reiner. And if you glue together enough of these, then you can actually get the point count. This is actually much easier to prove since it's sort of an average over the group, or it's a sum over the group. It's quite easy to prove. You don't need any of the fancy technology from Mintam's thesis. And once again, the combinatorics is actually quite a bit harder. But again, the DRR decomposition gives you these rational. They give you the non-crossing parking functions that Armstrong, Reiner, and Rhodes had defined.
This was my question in previous talk, I think. Yes, which is how to stratify your talk. How to stratify the.
I thought you meant the finite torus alone.
Huh?
I thought you meant the finite torus alone, the ungraded version.
Yeah, but this is if Q goes to 1, this will give maybe something like that.
You have a strategy. Okay.
So it's very hard to read off like Kreveris numbers and stuff.
Yeah.
You can, I mean, what I showed you where I was picking off the other A components, I'm getting that by gluing together some of these twisted bits. But to know which ones to glue together is not obvious.
Have a W action on this.
This is a lovely question. You're not the first one to ask me. And the answer is I think I could cook one up, but no. So the answer is no. But there's sort of they're natural things to try and do, but I haven't done them. Great. Other questions? Okay, so right. Okay, and here's an example from the paper of these parking functions, non-crossing parking functions. Right. So okay. So that's sort of the first example. So it's really powerful technology. I think I'm trying to sell this technique. The first story was just a self-contained thing about knots and so on. But now I'm really trying to sell this technique of getting combinatorics from these varieties. And so you can play this game in other ways. And so I'll give one more example, very short, and then I'll talk about some open things, and we'll be done. So if you can actually do this in the affine Weil group. Opdam has a trace formula for the Heck algebra, and as soon as you have such formulas, then you can start taking traces and cooking up these varieties for Catsmoody things. But it only exists in affine, and it has to be kind of a very special sort of element. So in this particular case, you can find two weights such that they satisfy the right condition, and then you can take their trace and you get something beautiful coming out. In fact, this recovers a formula of Haglund. So you hook up more combinatorics that people cared about using these braid varieties. And you can play this game. You just have to go out and find grades and do this and look up the varieties and then see what's indexing them and what's counted. So it seems quite flexible. So let me talk about some open problems in my last 5 minutes. So yeah, one of the issues is that it's when I said it's very powerful, sometimes it's pretty hard to find the bijections to the combinatorial objects that you want. So Paolo Galashan and Thomas Lamb had previously had this paper where they did some sort of version for rational Catalan numbers of type A, and they were trying to get dict paths out of it. And it's a struggle. They had to do it via some very some difficult recursions. Even this previous example where in this affine Weil group, finding a bijection, so it's somehow a Q analog again of parking functions. To find a bijection to parking functions would be lovely. I haven't found one. It is counted by this. What exactly is it? It's not so clear. So these are like very interesting. I mean, if you're a combinatorialist, they're very interesting problems that you can play with. Yeah, this is really this would be amazing, but I don't know anything. I don't know how to do it, and I don't know anything about it. But the idea is that if you were able to compute the mixed Hodge decomposition of these varieties over C, then you would actually pick up the QT Catalan numbers and QT versions of all of this. And so Thomas did this for our for the A2 case, where we glue together a bunch of these varieties. He was able to identify each of the pieces as examples he had worked out with Spire from a previous paper as varieties, and to show that actually they did respect the QT decomposition of the QT parking number. So this is surely going to be a way to get QT decompositions, and the problem is that I guess the technology for computing these things, the mixed Hodge decomposition is not there. But I've now said everything that I know on the subject. So yeah, this one's particularly annoying. So we have rational non-crossing objects, which I mean, I spent untold hours with Christian working to find, and what we don't really have are really nice graphical models, like a non-crossing partition as one would expect it to look. We don't have this. We have something else. It's a combinatorial object, but don't know how to make the combinatorics. This is from a paper with Brendan Rhodes and Drew Armstrong, where we made some sort of rational dodecahedron. So that would be the place to try and go, I think. Yeah, you could extend. So this is a place to go look for other elements that would have good properties, good enumerative properties, and you can do some calculations, and it seems promising. These periodic elements. Basically, the technology for Mintam's thesis applies to those, and so this is a natural class to look at.
Are Springer regular elements periodic?
I'm not sure. Yeah, that's a very reasonable thing.
I think they are every regular element. The power of it has to be equal to the full twist.
Okay, then yeah, they're even better than just periodic. Yeah, so periodic includes them. Thank you. And now we'll finish off with just this complex reflection group thing. So you can still do these traces in these Heck algebras of complex reflection groups. I mean, if you knew that those Heck algebras exist, as Yvan Morin was telling me, this is perhaps less settled than I was led to believe by the ability of my computer to do calculations. Anyway, so I have an undergraduate student who's doing these calculations for a long list of these spetzials. So there's an example. And oh, this would be fascinating. So of course you don't have the braid variety anymore, but you could still ask for the combinatorics of the decomposition to hold, and thereby hold in your hand some sort of combinatorial objects that would be indexing this decomposition of the non-existent variety. And so that would be something that would be interesting to look at from the point of view of combinatorics. I think that's it.
Very much. Other questions?
I guess that's in the very end, when you talk about possible generalization to complex reflection groups, you're only considering like well-generated complex reflection groups.
Special.
Special.
Yeah, even more special. Yeah.
So I have a question. So these things can also be thought as characters of some representations of spherical Cherenkov algebra.
Yeah.
And spherical Cherenkov algebra has a realization, so it acts on homology of affine Springer fibers. So is this related to affine Springer fibers?
This is the really, I think this is actually the non-crossing, non-nesting question. The thing is that my things are indexed by non-crossing objects, and I think the affine Springer fibers are indexed by non-nesting objects. So I think the difficulty of this combinatorial problem is reflected in the fact that these two varieties are actually different.
But they have the same number of points, yeah. But there is no maps, isogenous of any kind.
Okay, so Mintom and Thomas Lamb said this was related to, I'm going to say some letters like H equals M or something. No, I got them wrong. Okay. Yeah, that sounds better. Now I really have exhausted everything that I know about it.
Nathan, in type A, when you go to the rational case, so you've got A and B that are co-prime. I vaguely remember that in the rational Cherenkov picture, the finite dimensional representation for that parameter A over B, the Euclidean algorithm, that computes the GCD, they keep replacing the pairs, going backwards in the Euclidean. Does that happen here? Is there some geometry, when you replace the pair with the next one in the Euclidean algorithm?
Yeah, so there are funny things that happen. I think this is somehow like gluing a W naught or a full twist onto the word in the braid variety, and I think there are things that you can say, but yeah.
I wanted to ask if you have, so a lot of these things are when you start with a full twist and you take the trace for the thing that's associated to this as a loop. Do you have combinatorial interpretations for like maximal subwords for other braids?
So by other braids,
Other than the full twist?
these are not the full twist. These are powers of the
Powers,
combinatorial.
other than that, yeah.
No, I mean, it's one of the questions that I built one that was affine, and it's supposed to be counted by parking. And I mean, I don't know how to go to parking. I mean, it depends on what you consider combinatorial, maybe.
Is the problem that that thing is central, so you can calculate traces, and in the other way you wouldn't be able to do calculations, or you don't expect to have interpretations?
Oh, you could certainly do, the whole technology would work. It's just that the fact that it's a power of a Coxeter element makes the calculations able to go through a uniform way, because you have all of this vanishing, and you have this exotic Fourier thing, and you get all this vanishing, and it's just the exterior powers that show up. Yeah. So that's very special. But you would have similar special things for these periodic braids.